Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And here we're going to take a look at a fairly basic example that uses the Fundamental Theorem of Calculus, which is a definite integral. Here we are looking at an example of what's called a definite integral. The big difference between these and indefinite integrals are the numbers above and below the integration symbol. We call those the bounds of the integral. And when we look at a definite integral, it's a much different thing than an indefinite integral. The indefinite integral is a function. We call that the antiderivative. And the antiderivative is involved here. But what a definite integral actually is doing is calculating the area under a curve between the bounds a and b. Typically, a is what we call the lower bound. It's the one on the left in most cases. It doesn't have to be, but we like to do it that way. And b is the upper bound. That's the one on the right. So the Fundamental Theorem of Calculus, which sounds very important, and it is very important, is used to calculate this area. And it's actually a pretty easy calculation in most cases if you can determine the antiderivative function capital F of x. And what the Fundamental Theorem states is that the area under the curve between a and b is the antiderivative evaluated at the upper bound b minus the antiderivative at the lower bound a. This is just absolute survival stuff if you're going to be doing calculus from this point on, so you just have to know how to use this, and then we'll kind of talk a little bit about why does this all work at some stage. But if we look at a simple example here, we have a polynomial function, x squared minus 2x plus 3, and now we see the bounds on it are -1 to 4. Now the first part of the fundamental theorem is to understand what is that discussing. That's talking about the area underneath the parabola y equals x squared minus 2x plus 3 from -1 to 4. So let's have a look at that. So we see the curve here, and the area shaded beneath it is the area underneath the function but above the x-axis between the bounds -1 to 4. And so we see here we have labeled our lower bound a is -1, upper bound b is 4, and by definition a definite integral always describes the area beneath the function but above the x-axis. So in order to actually find this number, since geometrically we can't really do it, it's not a geometric shape, we have to use the fundamental theorem. And so step one of that is to do the antiderivative function. So just like we did before with indefinite integrals, we look at our function and say, well, that doesn't need a u sub or anything like that. That's just sum and difference rule and simple power rule and all that. So we have 1/3 x to the third minus 1x squared plus 3x. Now if this were an indefinite integral, if there were no bounds, we would put our arbitrary constant plus c there, and that would be our answer, that function. However, what happens in a definite integral, because it's f of b minus f of a, that arbitrary constant, which is the exact same number in this case, does cancel. So we don't write the plus c when we do a definite integral, to make a long story short. The notation of what we do next then is the vertical bar, which is in calculus means we're going to evaluate our antiderivative, and then we carry our bounds over to the vertical bar. So if we want to label what we've done so far here, this is our antiderivative function, capital F of x, and then we carry our a and b values over to our evaluation bar. So now it's just a matter of plugging in our upper bound first, capital F of 4, and then we're going to subtract capital F of -1. And so we put those into our function. Big F of 4 would be 64 over 3 minus 4 squared, so minus 16, plus 3 times 4, which is 12. That's our upper bound evaluation. And then we plug -1 into the antiderivative function, which is -1/3 minus a positive 1, -1 squared, plus a -3, so -3. So when you're evaluating definite integrals, particularly in polynomial cases, the arithmetic sometimes you get involved in a lot of fractions. You want to watch your signs because we are subtracting the antiderivative at the lower. So the typical things that happen, people forget to distribute to the negative and things of that nature. But if we just take our time now and evaluate this, we're going to get the area underneath that curve between -1 and 4. Now I could just go ahead and evaluate f of 4 and f of -1, but it's actually a little easier if I leave the fraction separate for a second and write that as 64 over 3 minus 4 minus a -1/3 minus 4. And then when I subtract, I can combine my fractions, -64 plus 1/3, 65 over 3 minus 4 plus 4, so it ends up being plus 0. And we get our area under the curve between -1 and 4 as 65/3, which if you want to write that as a decimal is 21 2/3 or 21.6 repeating. So we've done something that truly cannot be done without calculus here, which is to find the area under a curve even though it does not have a regular geometric shape to it. The tool that we use to do this, the Fundamental Theorem of Calculus, is absolutely critical at this point on in your calculus life, and you should definitely practice it a lot and get very good at it because you're going to see quite a bit of it from this point on. Very, very important application of the antiderivative. So that's the survival stuff. If you want to stay tuned, we're going to move on and talk a little bit about the proof of this. Why does this work? Because when you look at it, it's a great trick and it works all the time. But why does it work? So let's go and take a little look at the proof of this thing. If you want to learn more about the Fundamental Theorem of Calculus or taking definite integrals, you can find that on my calculus books available for a nice price on Amazon. Until next time, I'm P. Clark.